All right, welcome to Physics 1403. We're going to continue our discussion about all the information that light provides physicists and astrophysicists and astronomers as they go to study the universe. All right, and what I want to look at now is something called Wien's law. It is a relatively simple looking law, but it's kind of got some neat applications. All right, so when you look at these wavelengths that are being given off this continuous spectrum from a hot body, from a hot black body, all right, there are some wavelengths that are more energetic than others. And if you were to look at the wavelength that is delivering the most energy, it is the most common times the amount of energy that is on that wavelength. All right, that was what we call the wavelength of maximum emission. All right. So what Wien figured out is that if we look at that wavelength of maximum emission, that it's actually related to the temperature of that hot black body. All right. And that relatively simple translation is if we just take 0.0029 and divide it by that temperature. Now that temperature does have to be in Kelvin, by the way. Okay. The temperature in Kelvin, it will tell us the wavelength of what we're looking for. All right, so for example, let's say we were looking at a black hole. Now, black holes are, of course, famous for not emitting visible light. The reason is because the escape velocity of a black hole has so much gravity that the escape velocity of that object is greater than the speed of light. As a result, that black hole isn't giving off anything that we can see. However, oftentimes, black holes are surrounded by dust. You know, the universe, our galaxy included, is a very dirty place. There's lots and lots of dust everywhere. And the gravity of that black hole is so much that it compresses that dust and it compresses all of those gases that are swirling around that black hole. And the more you compress them, the hotter they become. Okay. So it's not uncommon to have a black hole where the temperature of that compressed gas is 10 million Kelvin. All right. To put this in perspective, the temperature of our sun is about 5,700 Kelvin. So we are talking about something that is incredibly hot. As a result of that, if we do the math on this, what we find is that the wavelength of greatest emission is about 2.9 times 10 to the negative ninth meters. Okay, because this wavelength does have to be in meters when we do it. All right, that is firmly in our electromagnetic spectrum. That is firmly in the area of X-rays. Okay, so X-rays, as in those exact same things. You go to the dentist, they put you in the machine, they go, right? High energy X-rays. Okay, so the reason we can't see even though you're right, we can't see the black hole, of course, because the gravity is so great. But we also can't see the gas cloud around them without special equipment because our human eyes are incapable of detecting X-rays. They're just too high energy. They would actually damage our eyes if they got into our eyes and they would damage the nerves and what have you, right? Overexposure to X-rays causes cancer, for example. It can cause cellular damage. All right, that's why the X-ray technician puts on the big lead vest and says, this is perfectly safe, and then goes and hides in another room. So we still can't see them, right? But let me show you something. X-rays. So we can't see them. So now we have telescopes that are designed specifically for X-rays. And a few years ago, they were able to capture a picture of an actual black hole. This is one of the earliest pictures of a black hole. And you can see this area. This is what we refer to as a false color image, where they take wavelengths that we cannot see with our eyes, and they assign them wavelengths of light that we can see. And so what they end up having is this is an area of X-rays and gamma radiation. And again, you have that black hole area in the middle that you can't see because the force of gravity is too great. So, what I found interesting about this picture is how asymmetrical it is. Um, black holes, as we'll talk later, black holes actually have spin, and we'll talk about that as well. Another picture I'm going to show you right here. This is an artist's conception of if we could see the X-rays, if we could see the gamma rays from all that hot gas, from all that hot dust being compressed. This is what an artist's conception of what we might be able to see if we could in fact see that along with the other things that are going on around that black hole. But again, the center of the black hole, nothing's coming out of that because of escape velocity. But using using Wien's law, we can kind of use that as to be able to detect and be able to find these black holes. Right. Wien's law is also used in your doctor's office. If you've ever gone to the doctor's office and they put the probe in your ear to figure out what your body temperature is, right? They're using Wien's law to, there's not like there's an expansion in there. You know, traditional thermometers use some sort of fluid like alcohol or in the old days mercury that would expand or contract based on temperature, and then they would be able to tell what the body temperature was from that. These things, they detect certain wavelengths, and then they run this through this equation here and interpret it as a specific body temperature. It's also the same thing, your HVAC people, when they come in and they go, boop, well, looks like your HVAC isn't charging or your heater's not working. They're using the exact same technology. So once again, astronomy used in the real world. So, all right. So you keep studying, and I'll talk to you in the next video.